Hello, my name is Matthew Rondinella, and this is Physics Lab number 2, Motion of a Falling Object. In this lab, there are several physics principles to discuss. The first is Newton's second law, which describes force as a product of mass and acceleration. It also states that a net force is equal to the sum of all individual forces in a system. The velocity and position update formulas detail how a specific final position and velocity can be calculated based off of the initial position of velocity plus the value times the change in time. And this is applicable to each individual frame in the video, which acts as a time interval. For drag force, there's turbulent drag from the air in this lab, and the force of that drag is the drag coefficient times the velocity squared with the direction opposite of gravity, because that is the acceleration due to gravity in one direction and drag in the other. For the specific measurements, the ping pong ball is 2.7 grams or 0.0027 kilograms. The door frame I used for calibration is 0.838 meters, and each time interval was 1 frame or 0.0333 repeating seconds. As you can see here, I have a tracker set up where I use the door frame as calibration and mark the individual points of the center mass of the ball at each frame. I tabulated the data and also received a graph that looked like a parabola, which implied some sort of net force. And in Google Sheets, I then transferred this data and made some slight adjustments to make the computation easier. So I took the time and the y position and subtracted both of these by the initial value to get an absolute measurement that started from 0. As you can see, time is positive because it is a absolute measurement, but the displacement is negative because the ball is going down, which is in the negative direction. Then, with this information, I was able to make a glow script simulation to model this motion. So I changed the initial conditions first by adding the mass of the ball, and I set the position and velocity equal to 0 because it was dropped from rest. Additionally, time is 0 and delta t is 1/30th of a second. Now the drag coefficient is either 0.00075 or 0, depending on if I want drag or if I want no drag. And the way I got this value was simply by guessing and checking values of b to make sure the final position of the glow script was the same as my actual tracker data. This is the kinematic calculation section. So as you can see, these three lines are calculating the net force by finding the gravitational force, which is just mg times the j hat for direction, the drag force, which is b times the magnitude squared, so bv squared times j hat, and you add the two together. Since this is negative going down and positive going up, it should be an accurate net force. I then used the velocity update formula and the position update formula to then get the new values of the ball at each time interval. For the arrow calculations, I simply use the position of the arrows and also the values I calculated before times arrow scale to get an accurate representation of the arrows. As you can see on this graph, I now have 3 different simulations that represent the motion of the ball. So this blue line here is the data from tracker, this red line here is glow script with drag, and yellow is glow script without drag. So as you can see, the largest vertical displacement is actually glow script without drag, which makes sense because gravity was the only force acting on the ball. So there was the largest net force directed downwards without the presence of air friction. So this calculation makes sense. The second one is glow script with drag. Now this makes sense as well because air friction was increasing, so the average net force on the ball was slightly smaller than if there was no air resistance because air resistance was countering the effect of gravity. So since this net force was smaller, there was a smaller vertical displacement. For tracker, you can also see the overall smaller net displacement, but at the individual values, it still remains slower than glow script. Now this may be due to imperfect data plotting. As you can see, these points may have not been entirely accurate on the center of mass, which is causing these discrepancies. But in addition, it can also be because in glow script, it assumed that the drag was always F equals BV squared. And in this case, the ball may have been traveling at different speeds in each frame due to my manual calculations, and that may have made the results inaccurate. Lastly, you have some conclusions. So the presence of air drag did cause the net force to decrease, and as time increased, this net force was smaller and smaller. And as you can see by the prediction in glow script, after 1 second of dropping hypothetically, the terminal velocity would be reached at about negative 4.5 meters per second, and this means there's zero net force on the system, or terminal velocity is upwards in magnitude equal to the downwards magnitude of gravity. Terminal velocity is also not affected by initial velocity. As you can see here, I changed the initial velocity to negative 2 meters per second in GlowScript starting here, and it was still negative 4.5 seconds reached as terminal velocity. So the initial conditions have no effect. Thank you for watching.